All right, it is that time. Uh, Welcome everyone to this session. I'd like to introduce Christoph Börgers, who's going to present on thoughts on the content of ODE courses. Go ahead.
Thank you very much. And thank you very much to everyone for coming to such a late session Friday night. I'm going to talk about various thoughts that I have about what one should do in ODE courses, or what I would like to do in ODE courses. And I'm also going to give you very brief sketches of a couple of things that I've written in the last year. And now I have to make sure that I know how to turn the page. Yes, I do. So just to introduce myself, I've done research linked with differential equations most of my life, but I've never taught the introductory ODE course at Tufts University where I teach until now. I'm teaching it for the very first time this spring. I have taught an upper level ODE course many times. I designed that class myself and I have taught it many times, but I've never taught the introductory ODE course, mostly for engineering students at Tufts and without a linear algebra prerequisite. So that's what I'm thinking about. I'm thinking mostly about content, not so much about methods of delivery, but mostly about what the content of such a course should be, in my view, or what I would like to make the content of such a course. Mostly I'm at this conference, though, to listen to people who have thought about these questions for many years, unlike me. I've thought, of course, about teaching many years, but I have not thought about how to teach an introductory ODE course for that long. My first guiding principle in designing this, and I think this is a bit preaching to the choir, because many people here say the same thing. Almost every equation should have an applications background in an ODE course. So I wouldn't use any equation like the one I wrote down here. I think that's just silly to use equations like that in a class on differential equations. For example, at the beginning of the course, we practice separation of variables with equations like this. This is a population growth equation with a declining growth rate. And I picked the parameters so that it's, roughly speaking, a decent model of the world's human population if you take T to be population in years, and P to be, I take population in billions. Or then we use the Gompertz law of tumor growth, which is like the logistic equation, except there is a logarithm that blows up at 0, so the growth is very fast at the initial time. And I make one exception in my class, namely I do talk about blow up in finite time, even though this equation dy by dt equals y squared that I use for that really also has no meaning that I'm aware of. But I can then say that there's a famous open problem in fluid dynamics to decide whether or not the Navier-Stokes equations allow blow up in finite time. And apparently that question is now much closer to being solved than it used to be. By Tom Howe and his collaborators at Caltech. One thing that I try to make really, really crystal clear throughout the course is that in real life, ODEs are solved numerically, not analytically. And that doesn't mean that I discuss numerical methods in great detail in my course. I discuss Euler's method, but for conceptual reasons. I think understanding Euler's method means understanding what an initial value problem is. And therefore, it's very important to understand Euler's method, I think, but I don't go into any details of any other numerical methods. I just mention that they exist. And I might mention the notion of order of convergence, but only very briefly and I don't expect the students to really absorb that unless they do by chance. But I do let the students use websites that plot solutions of ODEs for them from the first day on. And that also seems very important to me, that the students, and I have heard people do much more sophisticated things in that regard than I have been able to do so far. But I think it's very important for the students to be able to experiment and solve differential equations on their own graphically by just typing them into a website. It would be nice if they were actually doing Python programming, I think, but that's unrealistic, at least in my class. And so therefore, I just use a web page. And the web page that I use, I'm partial to because it was designed by my son. So Börgers is my son. So he made this web page with the help of ChatGPT. So this was fascinating to me because Benjamin doesn't really know anything about differential equations. And nonetheless, it took him only a few hours to make this web page. And why? Because the real heart of the code, the Python code that solves the differential equations, was found and put together by ChatGPT. So this is a website. There are many of these websites, I know, and where you can type in your equation and then you get a graph of the solution. The equation doesn't have to be autonomous, and this one obviously isn't. And then you get this interesting looking, very irregular solution. So now one thing that I've been trying to do, and I can't say that I can always do it very strictly, is to only introduce equations, first of all, that mean something, but second, from which one deduces something that one hadn't expected. And I find that hard to do. For instance, let me take the example of the logistic model. I talk about the logistic model, but I don't really know that one learns anything that is absolutely interesting about population growth from the logistic model. If a population were to grow according to the logistic model, then the interesting thing perhaps is that when the growth rates start coming down, that's half the carrying capacity. But that's an artifact of the precise form of the formula for the population growth rate. And no one takes that precise form seriously, of course. So I'm not sure whether I can actually defend speaking about the logistic equation from that point of view. It seems to me that maybe one doesn't learn much that one hadn't expected from that equation. But here's something that I found that I find more surprising. I take an equation, this website calls the unknown function y in all cases. So this is the population size. I take a population that has a seasonally fluctuating growth rate, and then I hunt at a certain season during the year. And that's reflected by this sine square term, which is just pulses of removal of individuals from the population. And I compare two cases, one where you hunt in the fall and the other one where you hunt in the spring, as it were. And the two hunting terms here are just phase shifted by half a period. And the interesting thing is that whether you hunt in one season or in the other season can make the difference between the population growing exponentially or the population going extinct. And if you had asked me that before I made up this example, I wouldn't have been quite sure how easy it is to make an example like that, or whether one can make an example like that, but there it is. So I like this example because one learns something that maybe many people naively thinking about it wouldn't have expected. Here's another example. This is a saddle node bifurcation that occurs because so it's if this term here, this is the differential equation down here. So this is a differential equation, a logistic equation with an Ali effect, so with an extinction threshold. And then I put a term in that reflects, again, hunting, periodic hunting. And at some point, it so happens that the hunting rate becomes so large that the system is pushed past a saddle node collision and the population collapses. So I don't know whether that's actually what happened to the passenger pigeon in the 1800s when the passenger pigeon fairly suddenly went extinct. But it's, I think, an interesting illustration for a class on differential equations, that catastrophic things can happen all of a sudden for hidden reasons, reasons that are in the dynamics but are not clear a priori. And the phase shift generated by an RC circuit, I think that's another example of something that one might or might not have guessed, but one can compute what the phase shift generated by an RC circuit is using integrating factors, which this, by the way, is almost the only example that I can think of where integrating factors actually give useful formulas. So James in his talk said that formulas are overrated, and I completely, closed form solutions are overrated, and I completely agree. These methods almost never work and in interesting ways. So, but here it does work in an interesting way. And then another principle to adhere to, of course, is that the applications should be honest. I read the essay by Rota, 10 Lessons I Wish I Had Learned Before I Started Teaching Differential Equations. I find things in there that I like very much, and I find things in there that I don't like and that I don't agree with. But this I do like. Rube Goldberg flows of salt water in communicating tanks don't serve any purpose. I have a quote here from a Calculus 3 exam. That's a real quote. I saw this exam. A flight travels along the curve given by these equations until time 4 pi. At time 4 pi, she has a heart attack and dies. I think that's silly, and it gives a bad impression of, it gives the impression that we have to fill the space with silly nonsense because we don't have enough to say. But of course, we do have enough to say, and we can have real applications. Another thing that I believe is that the applications should come from a broad range of fields, including natural sciences, engineering, and even social sciences in a single course. Rota says avoid word problems in that same essay. And one reason that he has is that the so-called word problems of a chemical engineer and those of an economic students aren't the same. And in this regard, I completely disagree. I think the economists shouldn't be protected from chemical engineering examples and vice versa. I think it's a good thing if they learn each other's problems. And that's, I think, why the math department should teach this course. If it were a disciplinary course with applications only from chemical engineering, then why not let the chemical engineers teach it? So now I'm coming to a couple of things that I have written papers about last year. And these are applications of ODEs, one in economics and one in political science even. So the first is an economic policy example, you might say. It concerns the question whether an income tax or wealth tax is more effective. And the first assumption here is that without government intervention, the rich will become richer until they own everything in the economy. And as the rich become richer, the pace at which they acquire further wealth accelerates because they can afford better lawyers and they have more lobbying power. And so the laws change in their favor, et cetera, et cetera. There is some theoretical justification of this in the so-called yard sale model, which is a model proposed by two people, actually. And I'm sorry, I forgot the name of the other person, but one was Chakraborty in India, and the paper is there, 2002. I will say very quickly, just because it's neat, what the yard sale model is. You have a number N independent agents. They are completely identical. They trade. And the assumption is that what happens in a trade is that someone makes a slight mistake and overpays for their car or underpays for the house that they buy. And therefore, wealth changes hands from one agent to the other. The assumption is that this is completely fair. So the direction of wealth transfer is determined by a fair coin. fair coin flip. But the amount is small if one of the two agents is poor. The amount is always so small that no one ever goes bankrupt in this game. And Chakraborty observed numerically that one agent will eventually own everything, and that agent will then remain the one winner. There will be one winner who will own everything, and everyone else will converge to zero. So one agent converges to having all the wealth of society, and the others converge to zero. This was observed, as I said, by Chakraborty numerically, and then my colleague Bruce Boghossian made a continuum version of it some years ago, 10 years ago. And I got into this because he's my office neighbor. And so then there was a probabilistic analysis of this problem by Choro 2 years later. And he might, in essence, he made the observation that this is just an application of the martingale convergence theorem. And with Claude Greengard, I constructed a proof that's more elementary and also somewhat more general. We don't need the martingale assumption, so we don't need the game to be fair. We can, in fact, assume that the game is a little bit stacked in favor of the wealthier agent, and of course, not surprisingly, the same effect happens if the game is less surprising when the game is already unfair in favor of the wealthier agent. But the proof that relies on the martingale property doesn't capture that case. And we have other things that we can do with our argument, like we can include effects like people become more cautious when they have lost money a number of times and things like that. So we can include memory effects. But then we reduce this to very simple equations. That's not in this paper do we do that, but we do it for the purposes of teaching ordinary differential equations. So the logistic equation would be a model of how the wealthy acquire more wealth. W is the wealth held by the very wealthy, and that wealth converges to one, is driven towards one meaning they own everything in society, with a rate that goes up as W goes up. So it's G times W. And this was actually derived from microscopic principles by Bruce Boghossian and his students in 2017. And then we compare what happens with income taxation and with wealth taxation. Income taxation really just means this: you put a factor in front there. The gain of the very rich people, DW, is damped a little bit. There is a factor less than 1 in front there. And this obviously just changes the time scale. Whatever happened before still happens, just a little bit more slowly. The other scenario is that you tax wealth rather than income, and some countries do this. Switzerland, I learned, does it, for example, and some countries in Europe do this, taxing wealth. And then you get an equation like this, and this, of course, is also a popular equation in population dynamics, and you get a transcritical bifurcation in this equation. If the rate at which you tax wealth is big enough, then if tau is greater than G, then the only stable fixed point, the stable fixed point to which every W will converge is 0. So you will abolish the class of super wealthy people. They will have 0% of society's wealth eventually. There's the transcritical bifurcation diagram. And this was in a paper that Bruce and I wrote for the Cody journal, just appeared last month. And we also have a review article that's a bit more general in Siam News last October about this. And very quickly, if I have the time to do it, I don't know, I have a few minutes maybe by my clock. I'll do a little bit my political science example. So this is based on a paper that I wrote with several other people for the American Mathematical Monthly, appeared in December last year. And we also made a Cody journal version of it that appeared last month. And we also have a Siam News article. Siam likes publishing things like that in their Siam News, I guess. So I don't have time to present the whole story, so I will present a drastic simplification of the American Mathematical Monthly article. We think about the following problem. We have a political spectrum, left-wingers to right-wingers. We think of this as the x-axis. Zero are the centrists. The left-wingers are on the left, the right-wingers are on the right. Everybody's views can be characterized by a single number, and whoever's number is negative is a left-winger, positive is right-winger. We now assume that there are three groups of voters, namely the hard right-wingers, which are, I'm sorry, I get it, have it reversed here. The hard right-wingers are at x equals 1, the hard left-wingers are at x equals -1. I'm sorry about that. Right and left are reversed here. And the people in between distributed evenly in the interval between -1 and 1. And now you have two candidates. One is a right-winger who is firmly situated at 1. And the right-winger captures the votes of the hard right-wing voters and some in-between voters. And you have a left-winger who is opportunistically maneuvering. So for the purposes of this discussion, I assume that the right-winger is not maneuvering, but the left-winger is. The left-winger changes position in order to capture more votes. And you can then write down expressions that plausibly reflect how many votes the left-winger would get. That depends on how close the left-winger is to -1. But there is a parameter there. That parameter reflects the degree to which the hard left-wing voters are willing to come out and vote, even if their candidate moves towards the center. And so gamma is a patience parameter. The bigger gamma, the more patient are the hard left-wing voters. They will come out even if the left-wing candidate has moved towards the center quite a bit. And then L also gets a fraction, the left-wing candidate also gets a fraction of the in-between vote. And that fraction, we assume, rises linearly with X. And you could put in constants here, and it doesn't change anything qualitatively. You get an expression like this for the share of the vote that the left-wing candidate gets. So this exponential term comes from the hard left-wing voters, and the X comes from the in-between voters, whom, for the purposes of this discussion, I'm going to assume are infinitely patient. They will vote for whoever is closer to them. In the monthly paper, we didn't make that assumption. If you plot this function and you vary the parameter gamma, you discover that there is a saddle node bifurcation or a blue sky bifurcation. If you decrease gamma, so you decrease the patience of those hard left-wing voters, suddenly a fixed point occurs, an attracting fixed point occurs on the left, which before wasn't there. So if gamma is slightly bigger, if their patience is slightly bigger, the left-wing candidates will move all the way to the right. It's in their interest to move to the position of the right-winger, actually. But as soon as their patience is just a little bit too small, there is a left-wing attracting fixed point and a repelling fixed point that come through a blue sky bifurcation. That's the conclusion. The conclusion from this model is optimal political strategies can depend discontinuously on the political environment. So I think none of this, of course, should be taken at all seriously, quantitatively. However, I think that might be a conclusion that is correct, that optimal political strategies can depend discontinuously on the political environment. And we have many other ways in which such discontinuities arise in a new paper that we're still working on. So this particular mechanism is by no means the only one that generates discontinuities in political strategy or in optimal political positioning. And that's all I have to say. And I think I have used up my time. So I'm not going to read the summary out loud, but just say thank you very much for staying this long.
Thank you so much for presenting. It was really interesting. We can keep this Zoom meeting open as long as you would like. So feel free, anybody, if you have questions, to ask them now. Today's whole thing ends officially in 5 minutes, but I think we can stick around as long as you would like to. But thank you for presenting.
Thank you. And Anna and I are actually within about, what would you say, 200 feet from each other, because we're both at Tufts University. I'm in a different building, but I'm in the math department building and she is in a different building. I see a nice message from Kurt Bryan, whose book I just received in the mail. I have it on my table here, actually. Thank you for the book. So, I just bought it from Simeon.
So Christoph, you mentioned that you have that you're interested in simulating differential equations on websites.
No, I'm just saying that that's how I do it in my class. I'm not actually interested in that subject in the abstract, but I just do it like that in my class because my experience is if I ask the students to write MATLAB code, then half of them have never done that before. And of that half, at least 1/4 will not do it by the end of the semester. So but I know there are many, many tools like that.
Yeah. Yeah, I've developed one myself, and so I thought what you said was interesting. So I hope you can make my talk tomorrow at 2 o'clock, because I can demonstrate it there. If you're
I'll put it into my calendar. I love this calendar that this conference has. So 2 o'clock tomorrow. Yeah, I'll put it in.
So do you teach all the different because you went through many different examples in different areas from economics to politics and things like that. Do you teach all the applications are you planning on teaching the different applications in your introductory course?
Yeah, so we have actually done the taxation example already. That was I think it was a homework. Yeah, it was a homework problem. So we do homework problems. We do worksheet problems that they work on in small groups. It's a big lecture class, but then they have small groups where they work on worksheets. And but that particular one was a homework problem. Yeah, I plan to do as much as possible of that this semester. But as I said, I've only done the beginning, only the first 3 weeks or 4 weeks of the semester so far. So we'll see how that goes. But I'm hoping to do that. I think that's the charm of this subject, right? That you can do applications from all sorts of different areas. So.
And this taxation, the taxation model has the parameters that allows to demonstrate bifurcations, right?
Yes, right. So with the wealth taxation, you get a transcritical bifurcation. With the other one, you get a trivial thing, namely the time scale slows down, right? With the income taxation.
So it introduces, with this example, you introduce bifurcations.
Yeah, I don't actually call it bifurcation. I just say determine what the equilibria are, determine whether they're stable or unstable, plot the equilibria as a function of the parameter, indicate in your plot whether they're stable or unstable, but I never say the word bifurcation, even though I'm using the book by Blanchard, Devaney, and Hall, and that book, of course, does say bifurcation, but I don't use that word because I do only those couple of examples, right? And so I don't need to give it a name, especially since in neither one of those two examples, anything is bi or anything forks, right? The bifurcation, the word bifurcation doesn't make a whole lot of sense for in either one of those two examples. So.
Great examples.
Thank you.
Do you volunteer on what classes to teach, or are they assigned to you?
No, so we express our preferences for which class we want to teach, and we often get what we want. So I wanted to teach this class. It's a natural thing for me to teach, but I'd never done it. And I asked for it. And in fact, I asked for it for another 2 semesters next year. So I'm going to teach it next fall, and it's already been more or less decided, I think, next fall and next spring as well. So that I do it 3 times in a row to figure out how I want to do it. So.
How many students are in the class?
160. So there's a class now. It's only it's gone down to 157 after 3.5 weeks or something like that. It has gone down to 157, but still 157. But then there are so it's a huge lecture hall, and I was really worried about that when the semester started. But I've never done that before. I have to wear a microphone in order to teach that class. But now I like that, actually. I like wearing the microphone because then I don't have to yell. I can just talk in a normal voice. And it turns out it's just fine. I have another app, also made by my son, by the way, that allows me to collect questions during the class anonymously. So, and they use it all the time. I keep my laptop open and on that page, and they constantly ask questions, and it's eye-opening to me. I started doing this when we were teaching during the pandemic, when we were teaching online. I was thinking, I cannot possibly know what the people in front of me are thinking or understanding, or what they're not understanding. But then my son made me this, he's into coding, and so he made me this, this app where they can anonymously ask their questions. Everyone sees what everyone else asks, but no one knows who's asking. And it's fantastic. You get like 20, 30 questions in a single class. Sometimes I have to postpone answering them to after class. I send them an email after class. I send the whole class an email and say, this was the question, this is the answer. But it's fantastic. It slows me down, but it's good. It's a healthy slowing down, I think. All right. So I will see you at your talk tomorrow and Victoria at her talk on Sunday.
Sunday.
Both in my calendar.
Thank you very much for a great presentation.
Thank
you, everyone.
Thank you. Good night.